Hello. Yesterday we have discussed the half wave rectifier and full wave rectifier. Today we'll discuss the bridge rectifier. So in case of the full wave rectifier with a center tap, we have seen that the full wave rectifier only makes the use of half of the transformer winding for the half of the time, and half of the transformer winding is not used for the half of the time. Therefore, the winding can be used all the time, or the transformer can be omitted. Okay, so why the transformer winding can be used only for the half the winding, and unnecessarily there will be losses. Therefore, either you use the winding for all of the time, or you just omit the transformer. So this is possible by using the bridge rectifier circuit. The circuit for this bridge is like this. So here we are applying the alternating supply voltage to this bridge network, and the current will flow. This is the resistor. So this is the IR, that is a current flowing through the resistor. This is also IR, and the voltage across this is VR. Okay. So here this is a diode D1, this is a D2, D3, and this is a D4. So the problem of transformer winding can be omitted here. Unnecessarily we require the transformer and we use half of the winding for half of the time, and it should be used for all of the time. That is not possible, so we have to use the bridge rectifier for the full wave rectification purpose. So in this case, when the potential is positive with respect to the B, so this is a point A and B. When the potential A is positive with respect to the B, then this diode D1 will conduct, the current will flow in this direction, it will flow in this direction, it will go like this, like this, like this. Again, this will conduct here, and it will go like this, and the circuit will complete. Okay. Again, when the potential B is positive with respect to A, then diode D2 will conduct, diode D2 and D4 will conduct, and it will complete the path like this. Okay. So the full wave type of the output is obtained, and therefore we can obtain the current flowing through the resistor as well as the voltage across the resistors. So the waveform of the when A is positive, when the potential of A is positive with respect to B, diodes this D1 and D3, D1 and D3 will conduct, and the current flows in a load. Then the potential of B is positive. Potential of B is positive with respect to A, diodes D2 and D4 conduct. D2 and D4 conducts and output is obtained. Output is current, and current flows in a load in same direction. So we are making use of both the positive half cycle as well as the negative half cycle. Therefore, the current I is taken from the supply is purely alternating. Yet the load current IR is unidirectional, but therefore basically we can show this like this. The current, supply current and supply voltage is like this. This is the supply voltage which is of alternating nature, and this is the supply current. Okay, this is the supply voltage, and this is the supply current. Now the voltage and current we get across the load is like this. This is the voltage across the load resistance, and this is the current across current flowing through the load resistance. And for the negative half cycle also, this is the voltage and this is the current. Okay, this is also VR and this is a IR. So here we are utilizing both half of the supply voltage, and we're getting the unidirectional voltage across the load and the unidirectional current across the resistance. So the efficiency of this network is, again, we have yesterday seen the efficiency is nothing but I DC square R into I RMS square into R. IDC square we have got, this is the 2 IM by Y square into R, and this is a IM by root 2 square R. This will get cancelled and we'll get this area by square. So again, neglecting the forward resistance of the diode, the voltage which appears across the non-conducting diode is equal to the supply voltage. So therefore, in this way, this is the full rectification without using the transformer winding, and this is called as the bridge rectifier circuit. Okay, now we'll consider one example over this. Four diodes used in the bridge rectifier circuit have forward resistance which may be considered negligible an infinite reverse resistance. The four diodes used in a bridge rectifier circuit have forward resistances which may be considered negligible. And infinite reverse resistances the alternating supply voltage is 230 volt and the resistive load is 46 ohm. Okay, we have to calculate number one, the mean load current. Number two, the rectifier efficiency. Number four, number one, solution. We have to calculate the mean load current. Mean load, what is given? Uh, RMS voltage is given. VRMS is given. It is a 230 volt. So for getting the IDC, that means the mean value of the load current, the mean value of load current is, in case of the bridge rectifier circuit, it is a IDC. IDC is equal to 2 Im 2 Im by pi. Okay, so here we have to, we require the maximum value of the current that we don't know, but we can find it from this RMS. VRMS is equal to Im by root 2. And here we have to calculate Im, therefore root 2 times IRMS. Now we have to calculate IRMS. We know the VRMS. VRMS is equal to IRMS into the resistance value. So from this we can calculate IRMS. VRMS is given, it is a 230 volt divided by this R is given 46, it is a IRMS, and we have to put this value in here, so we will get the maximum value of the current. So Im is equal to root 2 into IRMS. So root 2 into 230 by 46, therefore this value we have to put in the IDC. IDC is nothing but 2 times of Im into 2 times of Im by pi. Therefore IDC is equal to 2 times Im by pi. This 2 into 7.07 divided by pi. This is equal to 4.5 ampere. So this is a mean first answer, that is mean value of the load current. Now we will find the second answer. To find the rectifier efficiency. For rectifier efficiency, we require this. This is the formula. Okay. We know the IRMS. IRMS. To find IRMS, we know this is IRMS value, and we also require the IDC. We have got. Okay, so we can write here. This is IDC. We have got 4.6 square into resistance is 46, and IRMS we have got here. It is a 5 square into 46. You find this, we have got 181%. N is equal to 10% is equal to 81%. So this is the efficiency of the rectifier circuit. So this is we have got here 5, and that RMS value we have put here 5, and we have got this 81% efficiency. Thanks for watching the video.